Hello students, welcome to another video of calculus. Today we will discuss the squeeze theorem. Squeeze theorem. Squeeze theorem. The statement of the squeeze theorem is, suppose that x is equals to xn. This is the notation of sequence xn, comma y is equals to yn and capital Z is equals to zn are the sequences of real numbers such that xn is less equal yn is less equal zn for all n belongs to set of natural numbers. That is, the all terms of the sequence xn are either less than or equals to the sequence yn, which is again less than or equals to sequence zn. So the terms, that is x1 is less equal y1, x2 is less equal y2, x3 is less equal y3. Similarly, y1 is less equal z1, y2 is less equal z2, y3 is less equal z3, and so on. So if there are three sequences xn, yn, zn, and that three sequences satisfies this condition, that is xn is less equal, yn is less equal zn for all n belongs to natural numbers. Also, and the limit of sequence xn, limit n tends to infinity of the sequence xn is equals to limit n tends to infinity zn. That is, the limit of this sequence xn and this sequence zn are same. Limit n tends to infinity xn means limit of this sequence, and again limit n tends to infinity zn means limit of this sequence. If the limit of these two sequences are same, that is this limit of xn and limit of zn are same, then the limit of that sequence which is middle in between these, that is the limit of sequence yn is also same, and which is equals to the limit of these two. Then a sequence y is equals to yn. These two limit of these two sequences exist means these two sequences are convergent. Then a sequence yn is also convergent and converges to same limit as that of xn and zn. Y is equals to yn is convergent and limit n tends to infinity xn is equals to limit n tends to infinity yn, which is equals to limit n tends to infinity zn. The statement of the squeeze theorem is, suppose that xn, yn, zn are three sequences. The statement of this squeeze theorem is, there are xn, yn, zn are three sequences such that xn is less equal, yn is less equal zn for all n belongs to natural numbers, and limit n tends to infinity, that is xn is less equal, yn is less equal zn, and limit of these xn and zn exist, and limit of these xn and zn are equal, then yn is also convergent, and limit of the sequence yn is also equal to the limit of these two. This is the statement of squeeze theorem. Now we will prove this result. Proof of the squeeze theorem. Here we have given that xn, yn, zn are three sequence of real numbers, and xn is less equal, yn is less equal zn. Now let xn, yn, zn be the sequences of real numbers, be the sequences of real numbers such that xn is less equal yn is less equal zn. Suppose this is as equation number suppose star. This is the given thing. Also we have given that limit of this xn and limit of zn are same. That is, suppose the limit of both these sequences xn and zn are L. Let limit n tends to infinity xn is equals to limit n tends to infinity. This is the given limit n tends to infinity xn is equal to limit n tends to infinity zn, which is equal suppose L. This limit is equals to L. Now limit of these two sequences exist and which is equals to L. Therefore we can use the definition of epsilon delta, that is epsilon k definition. So that is the definition of limit. Therefore for given epsilon positive, there exists some positive integer k. There exists a positive integer k such that this mod of xn minus L is less than epsilon, and again mod of limit of zn is also L, so mod of zn minus L is less than epsilon for all n greater than or equals to k. This is the definition of limit. So using this definition we can write this mod of xn minus L is less than epsilon, also mod of zn minus L is less than epsilon for all n greater or equal k. Now this mod of xn minus L less than epsilon and mod of zn minus L is less than again epsilon. So we can use the property of modulus, that is mod of A is less equal C. So using that property we can write it as this minus epsilon is less than xn minus L is less than epsilon. Also we can use that property here, minus epsilon is less than zn minus L is less than epsilon. This is for all n greater or equal k as it is. Now if we add L on all these sides, we can write L minus epsilon is less than xn is less than minus L plus L gets cancelled, epsilon plus L, and again this L minus epsilon is less than Zn is less than L plus epsilon for all n greater or equal k. Now from this we can write this L minus epsilon is less than xn. By equation star we have xn is less equal yn, again that yn is less equal zn, and that zn is strictly less than 1 plus epsilon. So equation star, and suppose this is equation number 1, this is equation number 1. Now combining equation star and equation 1 we can write, now from equation star and equation 1 we can write this L minus epsilon is less than xn, xn is less equal yn is less equal zn is from equation star, and zn is strictly less than L plus epsilon, so L plus epsilon. So from this we can write this L minus epsilon is strictly less than yn is strictly less than L plus epsilon. So from this we get the all the terms of yn. This is for all n greater or equal k. This is for all n greater or equal k. So we can write this minus L minus epsilon is strictly less than yn is strictly less than L plus epsilon from this equation. So this implies L minus epsilon is less than yn is less than L plus epsilon. So subtracting L on all these sides, we get minus epsilon is strictly less than yn minus L is less than epsilon. So this is the, by using the property of modulus, yn minus L is less than epsilon. This is for all n greater equal k. This is by using the property of modulus. So hence we get mod of yn minus L is less than epsilon means this epsilon is the limit of sequence yn. Sorry, this L is the sequence limit of the sequence yn. This implies limit n tends to infinity yn is equals to L. This is our required proof. In this proof, we have just taken three sequences. This is the given thing. Also xn is less equal, yn is less equal, z is also given. Also the limit of these two sequences is equal, which is equal, suppose L. So this limit exists means this both the sequences xn and zn satisfies the definition of limit. So using definition of limit, we can write for any given epsilon positive, there exists a positive integer k such that mod of xn minus L is less than epsilon and mod of zn minus L less than epsilon for all n greater equal k. Now using the property of modulus, this by using the property of mod of a is less equal c if and only if minus c less equal a is less equal c, using that property we can write these two in this way. This is for all n greater equal k as it is. Now adding L on all these sides, so L minus epsilon is less than minus L plus L gets cancelled is less than L plus epsilon or epsilon plus L. Similarly here from these two equations, that is from equation 1 and equation star, we can write from equation 1 we can write L minus epsilon. From equation 1 we can write this L minus epsilon is strictly less than xn, but from equation star xn less equal yn less equal zn, and again from equation 1 zn is less than L plus epsilon, zn is less than L plus epsilon. So using these two equations and combining these two equations, we can write L minus epsilon is less than xn is less equal yn is less equal zn is less than L plus epsilon. So from this we can write this L minus epsilon is less than yn is less than L plus epsilon, and using that here we get mod of yn minus L is less than epsilon. This will give limit n tends to infinity yn is equals to L. Hence the sequence yn is convergent and converges to the limit L, and that was the limit of zn and xn also. So the sequence yn is converges and converges to the same limit as that of this limit of sequence xn and zn. Hence the proof of squeeze theorem. This is the important result. Now we will see some examples on this theorem. The first example is show that the sequence sin n upon n converges to 0. So that the sequence sin n upon n converges to 0. The solution, we know that mod of sin x is in between minus 1 to 1, as we know that minus 1 is less equal sin x. Instead of sin x we will write here sin n. Sin n is less than or equals to 1. We have to prove that the sequence converges to 0. By using squeeze theorem we will write that by squeeze theorem we have to find the xn and zn such that yn is in between xn and zn. Now if we divide throughout by n, then we get minus 1 by n is less equal sin n upon n is less equal 1 by n. So if we take xn is equals to minus 1 by n, yn is equals to sin n upon n, and zn is equals to 1 by n, then limit of this minus 1 by n and limit of 1 by n, if the limits of these minus 1 by n and 1 by n are equal, and then we can say that is the limit of this sin n upon n, and that limit must be our 0. Now we can write this as this minus 1 by n is less equal sin n upon n is less equal 1 by n, just dividing all the terms by n. So minus 1 by n is less equal sin n upon n is less equal 1 by n. So by squeeze theorem, therefore by squeeze theorem, we can find the limit n tends to infinity minus 1 by n is less equal limit n tends to infinity sin n upon n is less equal limit n tends to infinity 1 by n. If these two limits, that is limit of minus 1 by n and 1 by n, are exist and is equals to 0, then we can say that limit of sin n upon n is equals to 0. So this 0 is less equal limit n tends to infinity. Limit n tends to infinity, minus 1 upon infinity, something upon infinity is 0. So limit n tends to infinity minus 1 by n is 0. Limit n tends to infinity sin n upon n is less equal limit n tends to infinity 1 upon infinity is again 0. So this implies the limit of the sequence limit n tends to infinity sin n upon n is equals to 0. Thus this sequence sin n upon n converges to 0. Converges to 0. Hence the solution of this example. Now we will see the second example, which is the important one. Now the next example is show that the sequence xn, where xn is equals to sequence xn is given in the form n plus 1 bracket square 1 upon n plus 1 bracket square plus 1 upon n plus 2 bracket square plus up to 1 upon nth term is n plus n bracket square n plus n square, so that this sequence again converges to 0. Converges to 0. Now again the example is show that the sequence where sequence x is given in the form 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square, and we have to prove that this sequence is again converges to 0. Now we have given that, first of all we will write the given things here. Xn is equals to this 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square. So similarly, like previous example, we can write this 1 upon n plus 1 upon n plus 1 square is again, so if we write this, suppose this n plus n plus 1 and again suppose n plus n, then if we find the relation, then clearly this n plus n is greater equal n plus 1 and n plus 1 is greater equal n. If we add 1 in the n, then we get n plus 1. So n plus 1 is obviously greater number than n. So here n plus 1 is greater than or equals to n. Similarly, n is number, natural number greater than this 1, then n plus n is clearly greater than or equals to n plus n. If we take n is equals to 1, then clearly n plus 1 is greater than or equals to, or instead of greater than, we will just take n plus 1 is equals to n plus 1. So clearly this n plus n is greater than or equals to n plus 1, is greater than or equals to n. Similarly, we can write this n plus n is greater equal n plus 2 is greater equal again n plus 2 is greater than or equals to n plus 2. This n plus 2 is greater equal n, because we have to, if we add 2 in n, then that number obviously greater than n. So n plus 2 is greater equal n, and n plus n is greater equal n plus 2. So similarly, we can write this n plus n is greater equal n plus n is greater equal n. N plus n is equals to n plus 1. What we are writing here, n plus n greater than or equals to, greater than or equals to, here n plus n is equals to n plus n. So clearly this n plus n is greater equal n plus n, and which is greater equal n. Now if we take the reciprocal, this implies if we take the reciprocal of n plus n, then clearly that reciprocal, if we take the reciprocal, then the inequality changes. So if we take the reciprocal of this, suppose this n plus 1, not n plus 2. If we take the reciprocal of this first equation, then 1 upon n plus n is less than or equals to 1 upon n plus n is again less than or equals to 1 by n. So this inequality changes here. Similarly for n plus 2, 1 upon n plus n is less than or equals to 1 upon n plus 2 is less than or equals to 1 by n. Similarly here we are just taking the reciprocal, so this inequality again becomes opposite. So similarly this up to 1 upon n plus n is less than or equals to 1 upon n plus n is less than or equals to 1 upon n. For the this last inequality, we can write this 1 upon n plus n is less equal 1 upon n plus n is less equal 1 upon n. So here we can clearly say that 1 upon n plus n. Now if we take the squares, then there is no change. So if we take the square here, then again this equality becomes, if we take this square here, then this equality, there is no change on this equality. So this n plus n square is again greater than or equals to n plus n square is greater equal n square. So if we take the squares on both sides, because we need xn is equals to 1 upon n plus 1 square plus 1 upon n plus 2 square and so on. So we need these terms in the form of squares of this number. So here this, there is no change if we take this square, because clearly n plus n is greater equal n plus 1, then the square of that number is again greater than equals to the square of this number. So this inequalities becomes here. Now if we check this 1 upon n plus 1 square, here n upon 1 upon n plus 2 square, if we add these terms that are middle of these inequalities, so if we add this term with this, again adding these two with third term and so on, then we get this addition is equals to xn, because xn is 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square. If we add these terms, then we get xn. Similarly if we add these, then we will write, we can get this 1 upon n plus n square plus 1 upon n plus n square plus up to 1 upon n plus n square is less than or equal to, just adding the terms on left hand side, this, that is 1 upon n plus n square plus 1 upon this term plus this term. So addition of this term is clearly less than or equal to addition of these terms. So addition of these terms is 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square is xn. So instead of the addition of all these numbers, we will just write this xn again is less than or equals to the addition of these number, that is 1 upon n square plus 1 upon n square plus 1 upon n square. So we will get this as 1 upon n square plus 1 upon n square plus up to 1 upon n square. Now here we get this 1 upon n plus n square plus 1 upon n plus n square plus up to 1 upon n plus n square is less equal xn is less equal this. If we get the limits of this sequence and limit of this sequence is equal, then that will be the limit of our xn by squeeze theorem. So here clearly we can say that this 1 upon n plus n means 1 upon 2n, 1 upon 2n square plus 1 upon 2n square. So we can write it as this 1 upon twice n square plus 1 upon again this twice n square, n plus n is 2n plus square plus up to 1 upon n plus n is 2n square is less equal xn is less equal here 1 upon n square, 1 upon n square I will write one step 1 upon n square plus 1 upon n square plus up to 1 upon n square. Now here 1 upon 2 square, if we take the 1 upon 2 square, then the remaining terms are 1 plus 1 plus 1, these are n times. So if we take 1 upon n square and adding these n numbers, we will get n upon twice n square is less than or equals to xn is less than or equals to, again if we take the 1 upon n square common, then there are addition of 1 plus 1 plus 1 n times. So we can write this n upon n square. Now this 1 upon n square, n upon twice n square means n upon 4n square and n gets cancelled. So we can write it as 1 upon 4n is less than or equals to xn is less than or equals to n gets cancelled, so 1 upon n. Now if we find the limits here, limit n tends to infinity, so by squeeze theorem we can write, therefore by squeeze theorem we can write limit n tends to infinity 1 upon 4n is less equal limit n tends to infinity xn means here 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square is less equal limit n tends to infinity 1 upon n. Now limit n tends to infinity 1 upon 4 into infinity, 1 upon infinity is 0 is less equal limit n tends to infinity xn is less equal limit n tends to infinity 1 upon infinity is 0. So we can write this limit n tends to infinity xn is equals to 0. Thus our given sequence xn converges to 0. Thus the xn is equals to, the given sequence is 1 upon n plus 1 square plus 1 upon n plus 2 square plus up to 1 upon n plus n square converges to 0, converges to 0. Hence the solution of this example.